civil-based steel connection user. In this tutorial, I'm going to demo to you about brace connection transfer force. Transfer force, we also call it as a pass-through force. All right. So in brace connections, it's quite common. The structure engineer provides steel connection engineer with transfer force in the brace connection. So what is transfer force and how to interpret this transfer force in our program? So look at this steel frame, okay? When the lateral load is in this direction, like wing seismic is in this direction, this joint, okay, the brace connection on both sides of the column, there's a tensile transfer force, okay, from right to the left to the foundation, okay. So when you change the lateral force direction in this way, so there is a compressive transfer force, all right, transfer from the right to the left. So when it comes to the compressive transfer force, the actually it just squeeze these two sides uh, brace brace connection towards the column. It's not the unfavorable scenario, all right? But the most unfavorable scenario is the tensile transfer force when you the two sides of brace on two sides of column, they tear apart. They tear apart each other's. There's a tensile force mobilized in the horizontal beam. So these are the most unfavorable scenario, and it governs the design. So in our program, the brace connection we have under the design load, we have transfer force which is AB. It can take both positive and negative value. All right. So in transfer force, the in our program, the positive transfer force denotes the tensile transfer force, and the negative transfer force denotes the compressive transfer force. So come to the this one. As I say, the compressive transfer force is not a governing case. So pretty much we can ignore that. We only consider the tensile transfer force. But you know, when the engineer when the structure engineer give out the connection force, they just put plus minus. All right. So the brace force they put plus minus, and the transfer force they just put transfer force. They won't tell you it's a compressive or tensile transfer force, and there'll be uh, too many low combinations if you want to go to that detail. So for that reason, we only consider. I suggest my user only input the tensile transfer force, which means in this field always input the positive value. All right, that's a unfavorable scenario. Even the actual case is compressive transfer force, it's still safe. Okay, it won't fail your design because you consider the most unfavorable scenario. So repeat one more time. For my users of this program, we always input a tensile transfer force, which means in this field, transfer force field, although it can take both positive negative value, I suggest my user always input positive value for both two load cases. Okay, always input positive value. If there's a transfer force given out by structure engineer, the connection engineer always, for my program, always input positive value in these two fields. Okay, that will give you the most unfavorable scenario, and your design will be safe. Okay, so that's the sign of the transfer force. The Next, so like connection joint like this, okay? On a vertical continuous column, both sides have brace connection. Our program can handle right side like this, okay, or left side like this. When you have this type of connection, you just split this connection into two parts, left and right. All right. So the relationship between left and right is the transfer force. Okay. So basically, the force pass from the right to the left. If the foundation is here, always the force pass from right to the left. So you split this one into two parts and design them in two passes in our program. And you input the transfer force properly, you will just give you the correct design, the right way, the correct result of connection design. All right. So one more time, split the connection into two parts, the left and right part of the brace connection. And input the proper transfer force in each design pass. That will give you the right design, correct design of brace connection combined together. All right. So the last themes, the beam actual load. Okay. So come to our load input for brace connection. We have a brace connection. We have two load cases. Okay. Mainly target the brace connection, tensile, and compression. So the minus value is tensile. See tensile here. The positive value, the negative value is tensile. Okay, positive value is compression. So we have two load cases. Target tensile and compression. Two load cases. The design check for brace together is different. Okay, because you have buckling for compression. So you have tensile breakout for tensile case. So they are different. Don't think they are same. And the shear force pretty much will be the same for both scenario. And we have V-axis shear too, okay? V-axis. And also we have transfer force input. As I say before, always input positive value, okay, to be safe. And user might be wondering why there's no beam end, there's a beam end shear force, why there's no beam end actual tensile load input. As I say, the beam end actual tensile using the uniform force method. Okay, it's a result of horizontal component, the brace force horizontal component, and the transfer force result of these two get the beam actual tensile. It's calculated based on the other load input. It's not for input. If you input this value, input this value, there might be unbalance. Okay, at least join. So the in the low input, okay, we have brace actual low input, transfer force low input, but there's no. We have also beam and shear low input, but there's no beam actual low input. Okay, and ideally, the correct way is you input a brace force, you input a transfer force, but sometimes the structure engineer give out the beam and actual load. But sometimes they just give you out the beam actual load. If that's the case, connection engineer just take the beam and actual load as transfer force and input as positive value here. Okay, so as I say, if there's a beam and actual load, tensile complexive given out by structure engineer, the connection engineer just grab it, uh, input as transfer force. If that structural engineer give out both transfer force and the beam end actual load, that's not correct. Okay, and you can the correct way is give out transfer force, beam end shear load, and brace actual load tensile compression. Okay, so the last note, uh, it's always conservative to input the transfer force as positive value here. Okay, and that's for transfer force. So, and also if you have combined joint like this, left and right, just split them into two, to the left and right separately, input the proper transfer force, and that's the correct way to handle this design. Okay, now we now come to the actual design example. Okay, down below in the description area of this video, there is a link to download this PDF file. It's a working sheet for this conduction design. And we are going to demo you how to design these connection, and we split these connection come to column. We split this connection, brace connection, into left and right two parts. Okay, the relationship between these two sides is the transfer force, 250 kilonewton. We convert to imperial is 56.3 kips. Okay, so download this PDF file down below the link, and look at the right side first. Okay, that's 236 being to the 250 by 58 columns. There's end plate connection to the column flange that's welded to double angle brace. Okay, and there's a stiffener plate here. Okay, so look at this detail. Okay, now we will start. Okay, so we close this one. Okay, and that one you can click on that question mark, you get it, okay, right away. Okay, if you need some explanation, go. So before doing everything, go to setting, make sure it's American code and the imperial unit. Okay, then we I'm going to reset this one. I mean, change to M moment connection first. The idea is to reset everything, so we start from scratch. Okay, okay. So now look at this detail. It's double angle connections. We go to then we start from scratch. Brace connection, vertical brace, column at the left. Top army connect to flange. Yes, and these it's double angle, and the it's welded. Okay, 1/4 weld, 6-inch ROM. It's welded. Now it's bolted. We change to welded. Okay. Okay. Now welded. No, sorry. Okay. The angle is 47.5. Okay. Angle here to vertical line 47.5. 47.5. Okay. Now the brace section is okay. Canadian. Double angle, long leg vertical, Canadian, 127.89 half-inch, 127.89. No, long leg vertical first. Okay, 127.89 half-inch, 127.89 half-inch. Okay. Okay. All right, 3 parameters. Okay, the well size is 1/4, the length is 6 inch, the gauge is 1 and 5/8. Okay, the gauge is 1 and 5/8. So we have 1/4. Well, the gauge is 1 and 5/8, and the length is 6 inch. Yeah, so 6 inch, 1/4, gauge 1 and 5/8. We finish this one. Then we go to size, go to section. Okay, the column section is 250 by 58 Canadian section. Canadian. 250 by 58. The Bing section is 236. Bing section. Canadian. $236. Okay. All right. So this cassette. Okay, you see 1 inch the extension. I see the clearance, the tip to the top of pin flange. This is 2.5 here. There's no dimension. I say 4 inch. Okay, from the tip to the top of a pin flange. That's gusset geometry. Okay, go to gusset plate. Okay, you see that's 1 inch now. Okay, see the highlight. We'll highlight. We change this to for our details around 4 inch. All right. Okay, now the extension 1 inch, 1 inch. See the highlight 1 inch, 1 inch. That's good. The gusset plate thickness is half inch. Okay, half inch. Okay. Now I'll go to beam to column. All right. So for now, we see beam to column. It's unlikely we can accommodate for this being unlikely we can accommodate 3 loads of bolt. Okay, only 2 loads. For this case, okay, the beam to column and plate. The plate is 5/8. 5/8. 6 to 5. Okay. The when the beam is shallow, okay, guess at the column. Look at these uniform force measure. Okay, when this beam is very shallow, there's beam and tensile and shear. If this beam depth is like 8 inch, it's 236. It's W8. 2 loads. There are 2 forces, tensile and shear. Okay, and beam to column, beam to column. We have 2 loads of both. When there's a larger transfer force, and larger actual tensile, the uniform force, this one shear and tensile, uniform force method. Okay, when we have large transfer force, large actual tensile, you work out the actual beam end, actual and shear force, especially the actual load, is very large. Then there's no room for accommodating more rows of bolt, and this part most likely will fail the design. So to solve this problem, we have additional rows of bolt. Okay, additional rows of bolt. At the bottom, we also count these rows of bolt to beam column 2. So we have instead of 2 rows of bolt, we now have 4 rows of bolt contribute to the beam to column design. Okay, so for this reason, we have these options. Okay, one row more bolt. Okay, top and bottom. So these 4 rows of bolts all contribute to the beam to column. It will pass the design. So this one we have this one as 2.5, and we have stiffener plate. Okay, we have stiffener plate here. Yes, see here, stiffener plate. Okay, stiffener plate. Yes, and yeah, this one our number is 1.75, 0.75, and this one is 3.5, and gauge is 3.5, gauge is 3.5, and 2 rows, and EH is let's say 1.5. Okay, 1.5, and update. And the welding is all 1/4, 1/4, 1/4. Now being gets at the column. Now you see when these rows are both counted as beam to column. Okay, now for these Gasatu column, we have only 2 rows of bolt. Okay, so because okay, now this row has been counted as beam to column, so now I have 3. We only have 2 now. Okay, and this one D1 is 3.5, 3.5. This one is 1.75, 75. Okay, this one is 3.5, 3.5. The gauge is 3.5. This one is 1.5. Okay, the welding is welding is 1/4. Okay, update. Okay, now 3.5, 1.75. All right, so now we flush this one, gas out beam. Flush this one, and the welding is 5/16. Yeah, that's correct. All right, so now we pretty much finish brace part 1.62. We finished the geometry input. Now we go to load input. Okay, we have shear force. This being end shear to 28.8. We have tens brace actual 76.5. We have transfer force 56.3. Okay, so go to design load, and we clear everything to 0, and these brace actual load terms are first minus 76.5, and then this compression 76.5 positive, and the shear load 28.8. You see here it's 50%. Okay, 28.8. There's no minor x6 shear. The transfer force, as I say, always input positive value 56.3, and for both case 56.3. Okay, update. All right, 0.99. Okay, guess at the column. So we finished the right side welded. Okay, right side welded double angle brace connections. Okay, now we go to the left side. All right, so look at this detail. The difference is the beam size is different. 246. Okay, versus 236, and also the brace connection is by bolting. All right, the angle is the same. So now go to general. We'll do the left side now. Okay, colon at the right. Okay, colon at the right. Okay. Now the brace connection still double angle since it's bolted now, right? Now the section, the beam section is 246, okay, instead of 36. 246. All right. So now, yeah, brace. Now the three rows of bolt. 3 rows of bolt. The gauge. Okay. The gauge is 3 inch. Okay. 1 inch, 3 inch. Okay, the edge clearance, okay, is not that big now. It's 2 inch to this one. Okay, so we're going to, so the gauge is 3 inch for now. Copy. My suggest value is 2.5, but he used 3 inches. The gauge 3 inch. I would say this one 1.5. Okay, 1.5. 1.5, okay, 3 inch gauge, 3 inch gauge. Go to gusset, okay. Now you see this 4 inch, okay, highlight 4 inch clearance too much, okay. So our case, there's no dimension here. I would say 2 inch, okay. The tip to the flange plate is 2 inch, okay. See here, we say 2 inch. Okay, 1 inch, 1 inch, half inch. Okay, I think that's 2 inch now. Gusset to beam, copy, 5/16, yeah, copy, and flush this one, So now we pretty much finished the left side geometry input at 1/4, 5/16, 1/4, 1/4, 5/16. We finished geometric. Okay, now the brace load is same, 76.5. Transfer force is the same, 56.3, but the shear load is 33.8 instead of 28.8. Design load, okay, so 76.5 is the same. Okay, this one is you see here 34. Okay, 50%. Okay, 33.8, 33.8 because the beam size change. The transfer force always positive. It's still the same. Now we finished the left side. Okay, I finished the left side of the design. Okay, it's brace type. So finish this same transfer force. Okay, as the right side. So in until now, I show you how to design, how to split. Okay, the connections left and right side of the column, how to split it into two. Okay, like this case, split this one into two and do the brace connection left and right in two passes and input the proper transfer load. Okay, so that's the transfer force. If you are looking at the transfer force part, you can start at this point, and I already finished the tutorial on transfer force. Okay, so seems this connection there are two more. Let's sketch. There are two more connection. I just want to continue after that to show you some more feature of the program, because there's some unique part of these two additional extra connection. One is this brace connection to the weak axis. It's not like strong axis, weak axis of column, and also the brace tip encroach into the column flange line. Okay, and that one is around gusset plate. Okay, so horizontal brace. So I just do a quick run of these two extra connections. Okay, so look at this detail. If you still have time, let's move on this one. Okay, so look at this detail. I will do a quick run. All right. So general, this one now is connect to column web. Okay, right. So now the angle is 35.6. Okay, to vertical line. 35.6, 35.6. Okay, so the section, the column is 25, 12, 50, 58. The beam section is 236. Okay, 236. Okay. Now, look at this being to end plate. There's no additional roll at the bottom, so the actually end plate, the red one, extend to the flange of the beam fairly well. Okay, so for our case now, beam to column, we don't have this beyond beam flange. One more load. We have this case now. Okay, so we have end plate. Front view end plate extend to the beam flange. Okay, end plate extend to the beam flange. So that one is 3.5. That one's gusset to column. Now is 2.5, 2.5, 3.5. Okay, it's 2.5 now. 2.5 now. That one is 1.5. 1.5. That one is 3.5. Still 3.5. Gauge is still 3.5. 2, 1.5. This one is half inch, I believe, instead of 5/8, half inch. And this welding is 1/4. That's correct. Okay, side view. And the gusset. Okay, gusset. Now, see this highlight 2-inch here. Okay, highlight 2-inch. Now look at this different ones. Our tip of the double angle actually encroach into stick inside the beyond the flange line. Okay, and clearance to the end plate is 2-inch. Okay, it's not clear to the column flange line. Okay, it's clear to the end plate 2-inch. So we have option this 2-inch. If it's a positive value, it's clearance to the edge line. But if it's minus value, it's clearance to the beam to the end plate line. Okay, so for this reason, we input -2. It will move in. Okay, the brace tip will move in. Okay, it moved in already, but ends up this side is governing. So still fine, still okay. So now we go to brace. We see we copy everything. Okay, 3 of them, and the gauge is 2.5, which is correct. 3, and that one is 1.5. Let's put 1.5 for all of them. 1.5 for all of them. And the actually the sizing is different. 10276 sorry. Okay, sizing 102, 76, and 70.9. Okay, just sizing is different. Okay, okay, still 2.5. 10 to 77.9, still 2.5. Okay, 1.5. All right, so this cassette column. Now we have 1, 2, 3. Okay, 3 rows. Now we have 3 rows. Okay, 3 rows. Okay, and the this one is 2.5, 2.5. This one is 1.5. This one is 3.5. That one is 1.5. All right, so paint column 1/4 is done. Okay, so we input the design, cassette to paint. It's 1/4. All right, it's 1/4. Okay, and we want to copy and flush this line. Okay, copy. All right, we finished the geometry input. Now we want to input a load. Okay, we set everything to 0 first. So a difference is this case there's no transfer force. Okay, so actual tensile is 42.8. The being shear is 28.8. Okay, there's no transfer force, so we put 0 here. This one is minus 42.8 for tensile, positive 42.8 for compression. The shear load is 28.8, 28.8, 28.8. That's it. Okay, update, no transfer force, no VXX shear, 0.75. All right, so we finish these connection design. The unique feature is you learn from this example is the clearance gusset plate. Okay, the clearance of these brace tip. If input minus value is clearance to the inside end plate. Okay, if it's positive value, it's clearance to the column flange line here. Okay, so we can input positive, negative value here. Okay, we have two tips for that. Okay, 10 on 20, you will see that. So go to next. It's horizontal brace. Okay, horizontal. We'll run this very quick. It's right around gusset plate with cut out here. The column size. Section AA is here 250, 58. Okay. Okay. So now we go to the horizontal. This one is red plate. Okay. The angle is 33 degree. Okay. And it's WT now, 33 degree. It's WT now, not W angle. WT now. So the brace drop, okay, section AA, this WT brace, you see the brace drop is 4 inch, okay, 4 inch here. So that's, okay, just show you what's the brace drop, okay. Look at this, the brace. Okay, okay, we have this WT brace below gusset plate. There's a hidden line, okay, so again, this one, so the gusset plate is above the WT above gusset plate. We have WT below gusset plate. Below gusset plate, the drop is 4 inch. See the highlight? 4 inch. That's correct. Okay, so go to plan view. 33 degree. That's correct. And go to section. Sections. This one, as I say, the column. This column size is 250 by 58. Okay. All right. So very quick Canadian. $250 by 58. Okay. These being both horizontal and vertical being 236. 236. Okay. All right. And WT brace. That's 2 rows of bolts. Okay. 2 rows of bolts. That's section 15526. WT section. Canadian section. WT 15526. All right. So the gauge is 3.5. 3.5. Okay. Update. All right. So now, gusset to vertical. See now it's clear angle, right? It's connected by 76, 9.5. See here, 76, 9.5. The gauge is 1 3/4. Okay, and the welt is 3 side 1/4. So now it's clear angle below. The angle to gusset is by welded. Okay, the weld is 1/4 3 side. Okay, 1/4 3 side. 1/4 3 side. The section is 76 by 9.5 Canadian section. 76 by 9.5. All right. Okay. And the gauge, as I say, the gauge of this angle is 1 3/4, and the spacing 3 and 1.5 at distance. Okay, 1 3/4. Copy everything first. Okay, 3 it's 1.5. 1.5. Okay, and we did this D1 update. This D1 is this 2-inch. Okay. 1/4. I think we can copy everything from vertical to horizontal. Okay. General. Copy everything. 76. Copy. And the gusset plate. Okay. Gusset plate. Look at this gap. Okay, 4 inch. The cut out space. Okay, and 1.625. The cut out clearance. Okay, look at the highlight. Okay, 4-inch. All right, 1.65. Okay, it appears the sketch it's just 1.5 inch or 1 inch. That's not much. Okay, 1 inch for both case. So we probably put 1 inch for both case. The reason for this cutout is because 1 inch. Okay, see the highlight, 1 inch, 1 inch. The reason for this cutout, this distance, is to leave some space for access to tightening the bolt, the beam to column, like moment connection or shear connection, the tightening the bolt. So it's your choice. Okay, let's say I see the highlight of this one, 1 inch. No, this one 1 inch. If you need more space, you just input a longer number. Okay, so for our case, it seems there's not much room here. Okay, they're just 1 inch, probably 1.5. Okay, this one 2 inch. Let's put more. So we have more space. You can access this space to tighten the bolt. Okay, no conflict. Okay, another thing is this clearance, 2 inch. When we have to put the positive value now, because minus value appears to be clearance to the web. Now we have, let's say, 1 inch clearance to the flange edge line. Okay, we put the positive value 1 inch. Now 1 inch now. Okay, see here. All right, so 1.5, 1 inch. Okay, we up here we input everything. Okay, now see, this one is ½ inch. Okay, this side. This one is longer. Let's say 3 inch, 2.5 inch. Okay, so this one, look at this one is ½ inch. Okay, and that side is longer. See the highlight here. Okay, that side is 2.5 inch. Let's guess up. We pretty much input everything. Okay, we input everything. It's 3.5. It's a 3.5. Let's say brace. I believe it's 3.5. Yes. Now go to design mode. Okay. Now it's easy. 31.5 keeps tensile compression. Okay. 31.5 minus minus 31.5. That's tensile. Positive 31.5. That's compression. Okay. Update. All right. So we finish these horizontal blades. Okay. Let's finish these horizontal blades. Wrap around gusset plate with cut out. Okay. And that's that detail. So in this tutorial, we show you how to handle the transfer force, left and right side of the brace, left side, right side of the brace, connection design. Do it in 2 passes. Okay, input the proper transfer force. We also show you how to design the brace connection connect to the column web with axis. Also a bit around gusset plate with cut out horizontal brace, and all these 4 connections in say 10 or 15 minutes input times. Let's show how powerful our program is. It can help you out with the all types of connection scenario. Okay, and see you next time. Bye bye.